Welcome back, students. The last class we saw what are known as equivalence relations. We in fact finished with equivalence classes. We defined the equivalence classes. Let us begin with what they are. So, let X be any set and let R be a relation from x to x. Let R be an equivalence relation. What we wanted is an equivalence relation. So, now let x in x. We define a set box x with respect to this R as all those y in x such that the pair x comma y belongs to R. This was the set that we had, and in fact last time we conjectured that for any two distinct x and y, box x intersection with box y, either it is empty or box x equal to box y. Well, let us try to prove this. So, suppose let x comma y belong to x with x not equal to y. Now, suppose that box x with respect to R is not equal to box y with respect to R. We will have to prove that box x R intersection with box y R is empty, right, is not equal to this. So, claim is that box x R intersection with box y R is empty. Suppose not, that means what? That is, there exists y, or let us call it as z, in box x R intersection with box y R. Fine. Now, we have an element which is common to both box x R and box y R. So, that implies z belongs to box x R and z belongs to box y R. Now, by definition this is equivalent to saying that the pair z comma x belongs to R and the pair z comma y belongs to R. We know that R is an equivalence relation, therefore, this implies x comma z belongs to R and z comma y this belongs to R. So, this is because of the fact that R is an equivalence relation. Because it is an equivalence relation, it is symmetric. So, that implies that x comma y belongs to R since R is transitive. So, equivalence relations are transitive, and therefore, that implies that y belongs to box x R, and therefore, box y R is contained in box x R. Now, by symmetry of x and y, we have box y R equal to box x R. One can see that there is a symmetry between x and y, that means you can just interchange the role of x and y and prove that box x r is contained in box y r, and therefore, you have that box x r equal to box y r. Thus, box x r equal to box y r or box x r intersection with box y r is empty. Now, let us look at all the examples that we had last time, and let us try to write down what these equivalence classes for some of the examples. Example 1, one of the examples that we had was z, which is equal to all those set of all natural numbers, set of all integers, right. We had this, and then the relation that we had is r equal to all those m comma n in z cross z, with the condition that m is congruent to n modulo 9. This was one of the examples that we had. Now, let us try to write down all the equivalence classes for this relation. So, now let us fix, now 1 belongs to z. Now, let us write down the equivalence classes corresponding to 1. So, what is 1? Box 1 R is, we wanted all those integers n or m such that m is congruent to 1 modulo 9, or equivalently the difference between m and 1 should be congruent to 0 modulo 9, right. So, this means all those m such that m minus 1 is congruent to 0 modulo 9, right. So, m minus 1 is congruent to 0 modulo 9 is equivalent to saying that equivalently m minus 1 is divisible by nine. So, we are looking at all those integers m such that m minus 1 is divisible by 9. For example, let us look at an example 10, 10 minus 1, 10 is one such number. In fact, 10 minus 1 is divisible by 9. Now, by this it is more or less clear those numbers, it is going to be 10, 19. In fact, let us start with 1, because 1 minus 1 which is 0, 0 is divisible by 9, 1, 10, 19, 28, etc., which I will write it as 9n minus 1 such that n in z, right. All those elements of the form 9n plus 1, right. It is 9n plus 1 with n in z. So, therefore, box 1 with respect to this R is going to have 1, 10, 19, 28, etc. We have 0. Let us look at this one, the one corresponding to 0, which means that m should be all those n that are divisible by 9. Of course, we have 0, 9, 18, 27, etc. And I will just leave it with a final note saying that, note that there are exactly 9 equivalence classes. Well, now let us try to list down all the equivalence classes. The equivalence classes, these are the equivalence classes: 0, box 0, box 1, box 2, box 3, box 4, box 5, box 6, box 7, and finally box 8. And now one can notice that the equivalence class corresponding to box 9 coincides with box 0. Starting from 0 and up to 8, one can notice that box 1 and box 2 there is. So, whenever you have m and n between 0 to 8, right, including 0 and 8, if m and n are distinct, then there is no intersection between them. Let us look at one more example. The example that we had from geometry, let us look at R 2 minus 0. We had a relation R as all those pairs x 1 y 1 comma x 2 y 2 in R 2 minus 0 cross R 2 minus 0 with the condition that there exists a non-zero scalar alpha in R such that x 1 comma y 1 is equal to alpha times x 2 comma y 2, right. In fact, we saw that this R is an equivalence relation. Now, let us try to write down all the equivalence classes corresponding to this equivalence relation. Suppose x comma y, x 1 comma y 1, this is in, choose an R element from R 2 minus 0 0. Now, let us try to determine the equivalence class containing this x 1 y 1. Again, if x 2 y 2 and the pair x 1 y 1, if this is in R, that implies that x 2 comma y 2 is just an alpha times x 1 comma y 1 for some alpha in R with alpha non-zero. That means x 2 comma y 2 and x 1 comma y 1 lie on the same line passing through the origin. So, that means what? Given x 1 y 1, the equivalence class corresponding to the ordered pair x 1 y 1 is the straight line passing through the origin, except the origin, because we have removed origin from the original space. Thus, box x 1 y 1 with respect to R is the straight line passing through the origin with the origin removed. . I will just say a word about this, that this example plays an important role if one does what is known as the projective geometry. Now, let us go to the next important relation in mathematics of what is known as the functions. Most of you must be aware of the term function. This we must have seen in our elementary classes. So, but now the whole point is to define the term function in a more mathematical manner. Let us begin with the definition. A function f from a non-empty set A to a non-empty set B is a relation from A to B with the following properties. First one, domain of f should be whole of A. In general, we know that for a relation the domain need not be the whole space, but for a function it should be whole of A. Second, whenever A comma B1 in F and A comma B2 belongs to F, these two together should imply that B1 equal to B2, right. That means, for a given A in A, there one can associate only one element from the set B. That means, for a given A in the set A, there can be only one element B from the set B, such that A is related to B through this F. Fine. Now, let us look at some of the examples of relations that we had, and let us try to classify them whether they are functions or not. Let us look at the following example. Let A equal to -5, -3, -2, -1, 0, 1, 3 and 5. This was the set that we had, and the set B that we had was 1, 2, 4, 9, 16 and 24, 30. Let us have of these things. Now, we had a relation from B to A. Let us try to describe it in terms of the diagram. 1, 2, 4, 9, 16, 24 and 30. The other set that we had was -5, -3, -1, 0, 1, 3, 5. Now, an element B is related to A if so, for each B is B comma A is in R if B is of the form A square. So, 1 is related to 1. So, there is no element in A whose square is 2, but we have -2, we have both -3 as well as 3. So, these are the things. So, what is that we had? all those b comma a in b cross a with the condition that b is of the form a square. Now, let us look at this diagram. If you look at this diagram, 2, 16, 24 and 30, all these are in from B, but they are not related to any element from A. Also 9 comma minus 3 is in R and 9 comma 3 this is in R. So, these two, all these three things together imply that the relation R is not a function, right. Now, let us look at one more example. Let A equal to 1, 2, 3, 4, 5 and 6. Let R equal to all those A comma B in A cross A with the condition that B is of the form A plus 1. Now, let us try to draw this in the form of a picture. 1, 2, 3, 4, 5 and 6, and on the other hand you have 1, 2, 3, 4, 5 and 6. Now, notice that 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4, 4 is mapped to 5 and 5 is mapped to 6. Now, notice that the domain of R in this case is only 1, 2, 3, 4 and 5. So, which is not equal to the whole space A. Therefore, R is not a function. Now, let us try to write down one example for a function. Again, we had one of our examples, let us try to look at the other way. In fact, we looked at all those pairs such that the first element is the square of the second. Let us do the other way, that the second element is the square of the first, from let us say R to R given by R to R, the set of real numbers to real numbers, right, where f equal to all those pairs x comma y with the condition that y is of the form x square, right. You have this. Again, if you start writing your f is going to be a very huge set, but let us try to verify whether this is a function or not. Now, let us try to write down the domain of f. The domain of f, notice that for any x in x, now its square always makes sense, therefore, the domain of f is the whole of R. Now, again the second one, suppose that x comma y 1 is equal to x comma y 2. Now, x for a fixed x and for x is fixed and you have y 1 y 2. Now, the pair x 1 comma y 1 x 1 comma y 1 both belongs to R, right, both belongs to f, that is what we have. The pair, both the pairs x comma y 1 x comma y 2 belongs to f. Now, x comma y 1 this belongs to f, that implies y 1 is of the form x square. Similarly, x comma y 2 that belongs to f, that implies y 2 is of the form again x square. So, these two together implies that y 1 equal to y 2. Therefore, f is a function. Having said all these things, let us try to use some of the standard notation. So, let us write down in the form of a notation. Suppose that I have f from a to b, right, this is a function. In fact, this is the standard way of writing it, f from a to b. So, rather than saying that f is a relation from a to b with certain properties, this is the standard notation f colon a arrow b. This means that you have a function from a non-empty set A to a non-empty set B. So, that is the relation f is a function from a non-empty set A to the non-empty set B. Now, let us define one more quantity, what is known as range of a function. Suppose f from a to b, you are given a function, right, you have a function from a to b, then range of f, I will just write it as range of f, this is the notation, is defined as all those b in capital B such that, well, now let us try to. So, if the pair a comma b belongs to f, I will denote this a comma b belongs to f as this will be denoted as b equal to f of a. So, let us use the above notation such that b is of the form b equal to f of a. All those elements of b, capital B, with the condition that b is of the form f of a, or b is the image of a under the function f. So, by the term b equal to f of a, we mean that b is the image of a under the function f. Now, we had some functions. So, let us try to write down the range for such functions. Let us look at the function r to r given by f x equal to x square. This is exactly the function all those x comma y such that y is of the form x square. This is the standard way of writing. Now, let us try to write down the range for this function. Range of f is all those y in R with the condition that y is greater than or equal to 0. Now, how did I write that y is greater than or equal to 0? Which means, I will have to show that given any y in R with y greater than or equal to 0, one can always produce an element x in R such that this y which is greater than or equal to 0 is of the form x square. So, let y in R with y greater than or equal to 0. If y is 0, then one can choose x as 0 because 0 square is 0, right. So, let us assume that y is non-zero. Now, you have that y is non-zero, that implies that you have 2 square roots of y because and y is non-zero, and we know that y is positive. implies y greater than y non-zero implies y positive, implies there are exactly two positive roots, positive square roots, sorry, two square roots of y, namely plus root y and the other one is minus root y. So, let us choose one of them, let x equal to plus root y, that implies that y is x square. Thus, we have produced an x in R such that y is of the form x square. Thus, range of f is all those y in R with the condition that y is greater than or equal to 0. Let us look at one more example. F from z to z defined by f of n equal to n plus 1. Now, let us try, now here we notice that the domain of f is whole of z, and now let us try to write down the range of f. Range of f is going to be whole of z. That means, given any m in z, one will have to produce an n such that f of n is m. So, let m in z, I will have to produce an n such that f of n is m. So, let n equal to, let me choose n as m minus 1, that will implies that f of n, which is by definition, by our definition, which is n plus 1, but n, our choice of n is m minus 1, m minus 1 plus 1, which is m. Thus, range of f is whole of z. Now, let us try to look at some of the standard functions. The first one is identity function f x equal to x. Well, the domain and codomain, they are one and the same, f from R to R, f x equal to x. This is what is known as the identity function. F x equal to x. Now, so this function, so here what we have is that domain of f is whole of R, the range of f is again whole of R, and not only that, you have these two things. Now, let us try to draw the diagram of this function. You can notice that this exactly passes through the origin and it cuts the x axis at an angle of just 45 degrees, right, and this is exactly the straight line passing through the origin, making an angle 45 degrees with both x axis as well as the y axis. So, this is your x axis, this is the y axis, and this is the one that corresponds to y equal to x or f x equal to x. Now, let us look at one more function which we have already seen, that is f x equal to x square. We know that domain of f in this case is whole of R, and even the range of f is going to be all those y which are just positive or greater than or equal to 0. Now, the graph of this function, in this case you have this as the x axis this as the y axis, and therefore, the graph of this is going to be this one, right. It is going to be u shaped and attain 0 exactly at the origin, and then although the diagram that I have given here is not perfect, but still it actually touches the x axis only at 0 0 0 and at the remaining places does not touch the x axis. The next one, let us look at f x equal to sin x. Trigonometric functions, sin is a trigonometric function which will be introduced in some other lecture, but before that let us have a look at how this function looks like, which also you will have a chance to look at this function when you do trigonometry. This is going to be a 2 pi periodic function. This is how it goes. The peaks or exactly the maximum one that it can attain is 1, and they are attained at pi by 2, 3 pi by 2, 5 pi by 2, this is 3, right, and they attain the minimum at what are known as minus 1, this is 3 pi by 2, and again you will have all these things, and similarly on the left you will again have the same thing. Right, the maximum one that it attains is 1 and the minimum one that it attains is minus 1. This is what is known as the sine function. Let us look at the next example, f x equal to mod x. Here domain of f is whole of R, and the range of f in this case is going to be all those y in R with the condition that y greater than or equal to 0. This is the domain of R. Now, let us try to draw the graph of this function. This is your x axis, you have the y axis. In this case it is going to be two slanting lines, both making an angle. So, one makes an angle 45 degree, the other makes an angle 135 degree, or in the other way this angle is going to be 45 degrees. This is y equal to mod x. The next one, let us look at one more thing, f x equal to x cube. Here what we have is domain of f, in this case is whole of R, and again the range of f, one can verify in this case that the range of f is also going to be whole of R. And now let us look at the graph of this function. It is of this form. This is the, well, it is not going to be straight, but it actually it goes to infinity, the graph actually goes to infinity, that is what it says. Well, in the previous example let us try to explicitly write down what our mod x is. It is going to be x if x is greater than or equal to 0 and is minus x if x is less than 0. So, this is the function that we have. Now, with all these examples, now let us try to do some of the properties of functions. properties of a function. Now, first one, if I am going to have f from a set x to a set y, question is, suppose A and B are two subsets of x. Now, let us look at, we have two things, f of A intersection B and the other one is f of A and f of B. Look at their intersection. What is the relation between these two? Are these two equal? If not, which one is contained in the other? These are some of the questions that one can ask. Now, let us look at a special example from R to R given by f x equal to x square, f x equal to x square. Now, let me choose A as 0, 4, B as minus 4, 0. So, now by our choice of A and B, A intersection B is going to be just singleton 0. Fine. Now, let us look at f of A, which is going to be the whole of 0 to 16, and similarly f of B is going to be whole of 0 to 16, and f of A intersection B is going to be just singleton 0. Therefore, f of A intersection B is contained in f of A intersection with f of B, which in this case is exactly 0, 16, f of A intersection f of B. Now, is this always the case that f of A intersection B is contained in f of A intersection f of B whenever A and B are subsets of x? What is our claim? Our claim is that for any A comma B subset of x, f of A intersection with f of B contains f of A intersection B. So, to show that one set is contained in the another, we will show that given any element x in one of the sets, it also belongs to the other set. So, let x belong to f of A intersection B. Once you know that x is in the image of A intersection B under the function f, that implies that there exists x dash, or let me call this as y, so that you will have it as x in A intersection B such that f of x is y. Now, what we have is that x belongs to A intersection B, that implies that x belongs to A or x belongs to B. Once you know that x belongs to A, this implies that f x belongs to f of A, or you know that x belongs to B, that implies that f x belongs to f B. Oh, this is intersection. So, you will have and, right, you have and both the things. Now, you know that f x belongs to f A and f B, that implies that f x belongs to f A intersection with f B. That thus we have shown that. So, f x is exactly y, that implies y belongs to f A intersection with f B. Thus, f of A intersection B is contained in f A intersection with f B. Let us move on to second one. suppose A comma B are subsets of x. We have again f of A union B and the other one is f of A union f of B. Are these two sets one and the same? Is there any relation between these two sets? Is one contained in the another? These are some of the questions that one can naturally ask, and which one is true, and in fact only one can be true among these. So, which one is true? In fact, the claim is this: f of A union B is equal to f of A union f of B. We know that inclusion, that is inclusion is actually symmetric, that is in fact not just symmetric, it is, what should I say, well, we have this A contained in B and B contained in A, that forces us to conclude that A equal to B. Whenever you have two sets A and B, says that A contained in B and B contained in A, that forces us to say that A is equal to B. So, we will just use the same thing. So, let y belong to f of A union B. So, once you know that y is in the image of A union B under the function f, this implies there exists x in A union B such that y is of the form f x. Now, x belongs to A union B, that implies x belongs to A or x belongs to B. That immediately implies f x belongs to f A or f x belongs to f B. So, once you know that f x belongs to f A or f x belongs to f B, this implies that f x belongs to f A union with f of B, and f x is exactly y, that implies that y belongs to f A union f B. We started with an element y in f of A union B and ended by proving that y belongs to f A union f B. Therefore, f of A union B is contained in f of A union f of B. Now, let us prove the converse part. Let y belong to f A union f B. We have this. This implies that y belongs to f A or y belongs to f B. So, now let us look at the case y belong to f A, that implies there exists some x in A such that y is of the form f x. Now, on the other hand, y belongs to f B implies there exists x dash in B such that y is of the form f of x dash. Right. So, what it says is that we have x in A implies x belongs to A union B, x dash belongs to B implies x dash belongs to A union B. So, this implies f x belongs to f of A union B, and similarly the second one again implies f of x dash belongs to f of A union B. Therefore, y, which is same as f x, which is also same as f of x dash, this belongs to f of A union B. Therefore, what we have is that f of A union f of B is contained in f of A union B. In fact, we started with y in f of A union f of B and we ended with y in f of A union B. Therefore, f of A union f of B is contained in f of A union B. Therefore, f of A union f of B is equal to f of A union B. In the next class, we will see some more properties of functions and we will see some special classes of functions known as one functions and onto functions and give some more properties. Let us stop here. Thank you all.